Section 1.2, Phases and Classification of Matter. By the end of this section, you will be able to 1. Describe the basic properties of each physical state of matter, solid, liquid, and gas. 2. Distinguish between mass and weight. 3. Apply the law of conservation of matter. 4. Classify matter as an element, compound, homogeneous mixture, or heterogeneous mixture, with regard to its physical state and composition. 5. Define and give examples of atoms and molecules. Matter is defined as anything that occupies space and has mass, and it is all around us. Solids and liquids are more obviously matter. We can see that they take up space, and their weight tells us that they have mass. Gases are also matter. If gases did not take up space, a balloon would not inflate, increase its volume, when filled with gas. Solids, liquids, and gases are the three states of matter commonly found on Earth, Figure 1.6. A solid is rigid and possesses a definite shape. A liquid flows and takes the shape of its container, except that it forms a flat or slightly curved upper surface when acted upon by gravity. In zero gravity, liquids assume a spherical shape. Both liquid and solid samples have volumes that are very nearly independent of pressure. A gas takes both the shape and volume of its container. Figure 1.6. Solid. Has fixed shape and volume. Liquid. Takes shape of container. Forms horizontal surface. Has fixed volume. Gas. Expands to fill container. Figure 1.6. The three most common states or phases of matter are solid, liquid, and gas. A fourth state of matter, plasma, occurs naturally in the interiors of stars. A plasma is a gaseous state of matter that contains appreciable numbers of electrically charged particles, Figure 1.7. The presence of these charged particles imparts unique properties to plasmas that justify their classification as a state of matter distinct from gases. In addition to stars, plasmas are found in some other high-temperature environments, both natural and man-made, such as lightning strikes, certain television screens, and specialized analytical instruments used to detect trace amounts of metals. Figure 1.7. A plasma torch can be used to cut metal. Credit. Hypertherm, Wikimedia Commons. Link to learning. In a tiny cell in a plasma television, the plasma emits ultraviolet light, which in turn causes the display at that location to appear a specific color. The composite of these tiny dots of color makes up the image that you see. Watch this video. http://openstackscollege.org/L/16plasma. To learn more about plasma and the places you encounter it. Some samples of matter appear to have properties of solids, liquids, and/or gases at the same time. This can occur when the sample is composed of many small pieces. For example, we can pour sand as if it were a liquid because it is composed of many small grains of solid sand. Matter can also have properties of more than one state when it is a mixture, such as with clouds. Clouds appear to behave somewhat like gases, but they are actually mixtures of air, gas, and tiny particles of water, liquid or solid. The mass of an object is a measure of the amount of matter in it. One way to measure an object's mass is to measure the force it takes to accelerate the object. It takes much more force to accelerate a car than a bicycle because the car has much more mass. A more common way to determine the mass of an object is to use a balance to compare its mass with a standard mass. Although weight is related to mass, it is not the same thing. Weight refers to the force that gravity exerts on an object. This force is directly proportional to the mass of the object. The weight of an object changes as the force of gravity changes, but its mass does not. An astronaut's mass does not change just because she goes to the moon. But her weight on the moon is only 1/6 her earthbound weight because the moon's gravity is only 1/6 that of the Earth's. She may feel weightless during her trip when she experiences negligible external forces, gravitational or any other, although she is, of course, never massless. The law of conservation of matter summarizes many scientific observations about matter. It states that there is no detectable change in the total quantity of matter present when matter converts from one type to another, a chemical change, or changes among solid, liquid, or gaseous states, a physical change. Brewing beer and the operation of batteries provide examples of the conservation of matter, Figure 1.8. During the brewing of beer, the ingredients, water, yeast, grains, malt, hops, and sugar, are converted into beer, water, alcohol, carbonation, and flavoring substances, with no actual loss of substance. This is most clearly seen during the bottling process, when glucose turns into ethanol and carbon dioxide, and the total mass of the substances does not change. This can also be seen in a lead-acid car battery. The original substances, lead, lead oxide, and sulfuric acid, which are capable of producing electricity, are changed into other substances, lead sulfate and water, that do not produce electricity, with no change in the actual amount of matter. Figure 1.8. A. Pre-beer. Sugar. Carbonation. Ethanol. Beer. B. Sheets of Pb and PbO2, and H2SO4. PbSO4, and H2O. Figure 1.8. A. The mass of beer precursor materials is the same as the mass of beer produced. Sugar has become alcohol and carbon dioxide. B. The mass of the lead, lead oxide, and sulfuric acid consumed by the production of electricity is exactly equal to the mass of lead sulfate and water that is formed. Although this conservation law holds true for all conversions of matter, convincing examples are few and far between because, outside of the controlled conditions in a laboratory, we seldom collect all of the material that is produced during a particular conversion. For example, when you eat, digest, and assimilate food, all of the matter in the original food is preserved. But because some of the matter is incorporated into your body, and much is excreted as various types of waste, it is challenging to verify by measurement. 1.2.1. Classifying matter. Matter can be classified into several categories. Two broad categories are mixtures and pure substances. A pure substance has a constant composition. All specimens of a pure substance have exactly the same makeup and properties. Any sample of sucrose, table sugar, consists of 42.1% carbon, 6.5% hydrogen, and 51.4% oxygen by mass. Any sample of sucrose also has the same physical properties, such as melting point, color, and sweetness, regardless of the source from which it is isolated. Pure substances may be divided into two classes: elements and compounds. Pure substances that cannot be broken down into simpler substances by chemical changes are called elements. Iron, silver, gold, aluminum, sulfur, oxygen, and copper are familiar examples of the more than 100 known elements, of which about 90 occur naturally on the Earth, and 24 or so have been created in laboratories. Pure substances that can be broken down by chemical changes are called compounds. This breakdown may produce either elements or other compounds, or both. Mercury, oxide, an orange, crystalline solid, can be broken down by heat into the elements mercury and oxygen, Figure 1.9. When heated in the absence of air, the compound sucrose is broken down into the element carbon and the compound water. The initial stage of this process, when the sugar is turning brown, is known as caramelization. This is what imparts the characteristic sweet and nutty flavor to caramel apples, caramelized onions, and caramel. Silver, 1. Chloride is a white solid that can be broken down into its elements, silver and chlorine, by absorption of light. This property is the basis for the use of this compound in photographic films and photochromic eyeglasses, those with lenses that darken when exposed to light. Figure 1.9. A. The compound mercury, oxide. B. When heated. C. Decomposes into silvery droplets of liquid mercury and invisible oxygen gas. Credit. Modification of work by Paul Flowers. Link to learning. Many compounds break down when heated. This site. http://openstackscollege.org/L/16 Mercury shows the breakdown of mercury oxide, HgO. You can also view an example of the photochemical decomposition of silver chloride. http://openstackscollege.org/L/16 silvchloride. AgCl, the basis of early photography. The properties of combined elements are different from those in the free, or uncombined, state. For example, white crystalline sugar, sucrose, is a compound resulting from the chemical combination of the element carbon, which is a black solid in one of its uncombined forms, and the two elements hydrogen and oxygen, which are colorless gases when uncombined. Free sodium, an element that is a soft, shiny, metallic solid, and free chlorine, an element that is a yellow-green gas, combine to form sodium chloride, table salt, a compound that is a white, crystalline solid. A mixture is composed of two or more types of matter that can be present in varying amounts and can be separated by physical changes, such as evaporation. You will learn more about this later. A mixture with a composition that varies from point to point is called a heterogeneous mixture. Italian dressing is an example of a heterogeneous mixture, figure 1.10. Its composition can vary because it may be prepared from varying amounts of oil, vinegar, and herbs. It is not the same from point to point throughout the mixture. One drop may be mostly vinegar, whereas a different drop may be mostly oil or herbs because the oil and vinegar separate and the herbs settle. Other examples of heterogeneous mixtures are chocolate chip cookies. We can see the separate bits of chocolate, nuts, and cookie dough, and granite. We can see the quartz, mica, feldspar, and more. A homogeneous mixture, also called a solution, exhibits a uniform composition and appears visually the same throughout. An example of a solution is a sports drink, consisting of water, sugar, coloring, flavoring, and electrolytes mixed together uniformly, figure 1.10. Each drop of a sports drink tastes the same because each drop contains the same amounts of water, sugar, and other components. Note that the composition of a sports drink can vary. It could be made with somewhat more or less sugar, flavoring, or other components, and still be a sports drink. Other examples of homogeneous mixtures include air, maple syrup, gasoline, and a solution of salt in water. Figure 1.10. A. Oil and vinegar salad dressing is a heterogeneous mixture because its composition is not uniform throughout. B. A commercial sports drink is a homogeneous mixture because its composition is uniform throughout. Credit A left. Modification of work by John Mayer. Credit A right. Modification of work by Umberto Salvanin. Credit B left. Modification of work by Jeff Bedford. Although there are just over 100 elements, tens of millions of chemical compounds result from different combinations of these elements. Each compound has a specific composition and possesses definite chemical and physical properties that distinguish it from all other compounds. And, of course, there are innumerable ways to combine elements and compounds to form different mixtures. A summary of how to distinguish between the various major classifications of matter is shown in Figure 1.11. Figure 1.11. Matter. Does it have constant properties and composition? Yes. It is a pure substance. Can it be simplified chemically? No. It is an element. Can it be simplified chemically? Yes. It is a compound. Does it have constant properties and composition? No. It is a mixture. Is it uniform throughout? Yes. It is homogeneous. Is it uniform throughout? No. It is heterogeneous. Figure 1.11. Depending on its properties, a given substance can be classified as a homogeneous mixture, a heterogeneous mixture, a compound, or an element. 11 elements make up about 99% of the Earth's crust and atmosphere. Table 1.1. Oxygen constitutes nearly 1/2 and silicon about 1/4 of the total quantity of these elements. A majority of elements on Earth are found in chemical combinations with other elements. About 1/4 of the elements are also found in the free state. Elemental composition of Earth. Element. Symbol. % mass. Oxygen. O. 49.2. Silicon. Si. 25.67. Aluminum. Al. 7.5. Chlorine. Cl. 0.19. Phosphorus. P. 0.11. Manganese. Mn. 0.09. Iron. Fe. 4.71. Calcium. Ca. 3.39. Sodium. Na. 2.63. Potassium. K. 2.4. Magnesium. Mg. 1.93. Hydrogen. H. 0.87. Titanium. Ti. 0.58. Carbon. C. 0.08. Sulfur. S. 0.06. Barium. Ba. 0.04. Nitrogen. N. 0.03. Fluorine. F. 0.03. Strontium. Sr. 0.02. All others. Dash. 0.47. Table 1.1.